Good afternoon. It is water treatment class out of Introduction to Environmental Engineering. My name is Jaeweon Cho, who instruct you to understand what water treatment is, what treatment can be achieved to remove contaminations out of the source water, including river, lake, and even seawater. We are going to get to that 2 weeks after. So last time on Tuesday, so we discussed about what our purpose with water treatment, and also we would like to understand what process is appropriate and proper to remove each contamination from particle to colloid and organic matter and ions and salt as well. So the last time we discussed about this table with the particle and colloid and organic matter and ions and salt. And the first particular matter, and we discuss about the colloid matter and ions and salt. In size, a particle generally larger than micro size. So I already mentioned from a long time ago, very famous the paper about the particulate matter with the specific the magic number with which we can distinguish colloid to be suspended forever virtually and be settled down, which is approximately 0.45 generally. But depending on size, this size of 0.45 vary under different conditions. So the rod type, and circular types, rectangular types, and depending on those shape, the particle move differently. We also have different conditions of flow of the fluid. So if a fluid flow, the particle may move differently. From a particle to being the place in the stable conditions without any flow. So with the flow, we have another forces. The name tangential flow, the influencing forces. So to be added to the buoyancy force and the gravitational forces as well. So to combine everything, so we can calculate what the resultant forces can exert on the particle. So this is another, once again, the class of the detail, the principles, the mechanics, and the theories as well. So this is only introductions to environmental engineering. Out of this, we discuss about water treatment. So then we would like to understand in a conceptual way instead of a calculation and others that stuff as well. With your examinations, I also ask you conceptual questions. So you might have the few calculation, but not much. So very basic calculation. Calculation is actually for another interpretation of your conceptual statement. So if I ask you if I give you some contaminant of a particle, colloid, and ion with certain levels, and then you decide conceptual treatment, the processes to remove all those based on your interpretation and analysis and understanding as well, conceptually, right? So you may do that. So this is what I'd like to ask you So with the conceptual knowledge, conceptual understanding. So the particle, so we have a particle, so we would like to remove before we drink it. So what kind of process do we need? So time. So we need the time to wait until all the particle removed out of water. So that's the more than enough. If you have the colloid, the time is not, does not matter, because their colloidal the matter, they can be suspended forever, because there is a kind of the balance of forces to exert on that surface of the colloid, and including gravitational buoyancy and other tangential forces. Okay. So then we need something to do. So today we would like to discuss about and to take some action of the process called coagulation. Okay. Coagulation, or colloid. Coagulation process for colloid. That's the one process. Because the colloid, each colloid, the particle, we generally do not call the particle, but sometimes we call the particle as well. So particulate colloid and whatever you would like to mention. And then we will get to that in a few minutes. And organic matter, as I already mentioned, that then organic matters are itself and themselves are not toxic. So we can eat, we can drink without any treatment. But with this one, reacted with disinfectant, the chemical of disinfection. So it can produce a toxic material sometimes. With the chlorine and ozone, we would like to discuss today, and then we can drink it. And then we have ions, sulfate, phosphate, ammonia, and nitrate, and many others. So some ions are toxic and the other one is not. So we would like to remove it, but not easy at all to remove these ions. And finally, we have a salt, sodium and chloride. Sodium, Na plus, chloride ion, Cl minus. Then mostly with the seawater, we have a lot of high amount of tens, 10,000s, a couple of thousand milligram per liter, ppm levels of sodium and chloride. We cannot drink it. If you drink it, you can actually worsen your thirsty, right? So we have to remove sodium and chloride out of seawater to be safe drinking water. That's the we call the desalination process. All of these, they have the from particle, colloid, organic matter, ions, and salt. Everything have their own index. Their index, which is a criteria with which we can decide, we can determine, we can criticize, we can estimate whether the water is clean or not. So individual index. So a scientific index, engineering index, the measurement index we have. So for example, particle. So how many particles do we have? That's the index. So 10 particles per liter, 100 particles per liter. So that's the index. So number per liter. So that's the index. How about the colloid? What could be, do you think? So there are standard measurement method, standardized, of course, with various water qualities. But colloid, what could be an index? That's the turbidity. So in Korean, turbidity meter. So we have a turbidity meters. But so of course it is very easy to measure. So if you take a sample and you put the sample into the instrument of the turbidity meter, so turbidity meter show you how turbid your water is. How turbid water is. So coffee, if you put the sample of the coffee into this turbidity meter, its turbidity is very high. If you take a sample from Nakdong River and Han River, turbidity much less than coffee, but not enough to drink it. So the unit of the NTU. Unit is NTU. The NTU is the unit of turbidity. Okay, so high turbidity, it means dirty water from the colloid. Dirty water from colloid. How about the organic matter? How about the organic matter index to decide how much they contaminated organic matter? What do you think? So if you take the sample from the Nakdong River, so we have, of course, the measurement tool to measure how much we have organic matter in water taken from Nakdong River. Organic matter, how can you measure? Total organic carbon in the unit of milligram per liter. Total organic carbon, TOC. So we have a TOC meter. So if you take a sample, again, to put those sample into apparatus of total organic carbon measurement tool, TOC meter, of course we have in at the environmental engineering department. If you would like to measure certain TOC level, then you can bring the sample to the department, 11th floor, and then you can measure it, milligram per liter. So to help you how much we have for Nakdong River, can you guess? Can you guess which number correspond to Nakdong River TOC? Nakdong River TOC. Okay, thank you, Chajuno. Okay, so then you are first. You deserve to know. Nakdong River is about 5 milligram carbon per liter. Milligram per liter. So if our Nakdong River has only organic matter with a concentration of 5 milligram per liter, other contaminations are not included. We drink Nakdong River, that's fine. Okay, organic matter is not toxic at all. That's the naturally occurring matter, organic matters. But some from industrial factories, they might be toxic, but naturally occurring organic matters are not toxic at all. So for example, if you go to Amazon, Amazon River, can you guess how high of this TOC concentration for the water from Amazon? Please guess. Yeah, of course, higher than Nakdong. How high? Okay, please. 2 million per liter. Okay, 2 million per liter is very low. So if you go to Seomjin, so there might be that level, 2 million per liter. Okay, 10, 50, 30. How about 100? That's right, 100. Amazon is 100. Okay, so if you see some drama and the movie with the background Amazon River, what could be the signal? How high? So how much high represent those qualities with contamination of organic matter, even if not toxic at all, but with approximately 100 milligram per liter carbon for Amazon is color. Okay, almost yellow and brown, color. So there, okay, brown color, thank you. So there, the people swim. During swim, they can drink, right? So after swim, they kill? No. So at 100 milligram carbon per liter of TOC from water from the Amazon, that's fine. That's fine, right? So the Nakdong River, how about it? Nakdong River 5, and Amazon River 100. So a different color. So it looks like it. If you see the water color of the Nakdong River as opposed to Amazon color, which one seems to be cleaner than the other? Which one is cleaner? Okay, Nakdong River seems clean, but very opposite, right? Very opposite. Why? Nakdong River actually may have a lot of toxic ion from Gumi industrial sectors, Daegu industrial sectors, Busan area, a lot of wastewater treatment connected to this Nakdong River. But Amazon, I'm not sure exactly, but maybe and probably, I guess. So all the organic source are from the forest, right? The forest. So Amazon River is absolutely clean. So TOC, you may ask me, so the TOC from wood and forest, that's right. Okay, that's the humidification process. Humidification process with wood and root and levers. Okay, to make organic matters. Okay, this is a very interesting area. So in January, water treatment plant to provide our tap water, stormwater, tap water, so that they don't remove organic matter. They don't remove organic matter in Korea, in other countries as well. Why? Organic matter is not toxic at all. But the Korean water treatment plant to provide the yellow color of tap water, do citizens accept to drink those water as it is? without any further treatment? No, right? No. How about Brazil? So if they take water from the Amazon River with the high, as high as with the value of 100 million per liter, with a yellowish brown color of the water, but cleaner than ours, but they provide those water to citizens. The people may be hesitant to drink those water, even if this is very safe. From the analysis based on a scientific measurement, but due to color is important. Color is aesthetic. Okay. Also in California, in US, I'm not sure you've been there. The Disneyland in California, Orange County. Why their name of the village name is Orange? Have you heard about it? US Orange County in California. So their groundwater has groundwater with the color of orange. Okay, like Amazon. So their measurement, the TOC is about 50. TOC is 50 million per liter, because their groundwater has a lot of organic matter in it. But those water is actually very clean, except those organic matter. Not problematic at all. Okay, so water treatment is kind of the complex mechanism to remove all the organic matter, even if they are not toxic, but we have to remove it. Organic matter is very small, right? Very small. The colloid we can do through coagulation process. We are going to that in minutes, but organic matter is smaller than that. The colloidal matter, we use the size of a meter, micrometer, nanometers, and so on, but we don't use size of a meter with organic matter. Instead, we use molecular weight. So size unit, what could be a size approximately for the particle? Micro size, right? Micro size. How about the colloid? Less than 0.45. Okay, the particle. Higher than meter, right? How about the colloid? From our Einstein, right? 0.45 micron. So that's the once again, every filter to prepare sample prior to your experiment with water, you have to use 0.45 micrometer filter to prepare your sample, because you would like to remove all the particle. Okay, that's why. How about the fine particle, 미세먼지? How about our fine particle? 미세먼지, size of 미세먼지, size of our fine particle from China, from domestic sources. What's the size? What's the average size of the fine particle, 미세먼지? 0.1? 0.1? Are you sure? Fine particle. 10 micron, yeah. Who was it? Jung Jin-hee. Yeah, that's right. The average size is 10 micron. That's the 미세먼지, the fine particle. How about the 초미세먼지? Super fine particle. 4, okay. A little bit less, 2.5, 0.1, okay, 2.5, 2.5 in Korea, 1 in US, 2.5 in Korea, 1 in US. Why different? Why different? So that much we are not ready for that. We are not ready for that. So China and Korea, we use 2.5, 2.5 and 10, 2.5 and 10. But actually, the fine particle, 초미세먼지 in Korean, is actually less than 1 micron, sometimes 0.1, 0.45, similar to Einstein size. So if you inhale into our intestines, into our blood, nano size of a fine particle in air penetrate our cell barrier, cell membrane. That's the very toxic. So that's why we conserve. Those presence in the air. Okay. So how about the organic matter size? Size of organic matter. Which unit? Meter? Micrometer? No, actually. Okay. What kind of unit to measure size of organic matter? I think this is very important. So why not? Why not meter? Why not the nanometer? Why not the micrometer used to measure size of organic matter? Why? Why not? Have you heard about it? Have you taken organic chemistry? So which unit we've been using to measure the size of organic chemical material? Which one? Dalton, right? Dalton unit. So in molecular weight. Molecular mass. Molecular weight or molecular mass is the more strictly molecular mass is right terminology, but in a custom way we've been using molecular weight as well. MW, right? How about the water? What is the size of water? What is the size of water? What is the size of water? Anyone? Right? 18 Dalton. So there might be the size in the unit of Armstrong and nanometers and micrometer, 10 to the minus 13 or 10 to the minus 14 meter. But we don't use that unit with water, for the water. Instead, we use 18 Dalton because molecular mass of hydrogen is 1. Molecular mass of oxygen is 16. So combining those one is 18. Okay, so that's the indicative alternative size unit of the organic matter. So water is not organic, but reference to that. How about the methane? How about the molecular weight of methane? How about the methane size of methane? 16. So not exactly comparable, So in that, the size between the methane and water, which one is bigger than the other? Water, right? Water. What could be the size? What could be size? What could be size of this one, this organic matter? What could be a size of acetic acid, right? That's right. So how much big of this particle, of this organic matter compared to water? Approximately four times, okay, 3 times, 3.5 times. Okay, if I say our organic matter in water to be removed, if you have a certain organic matter in nakdong river with organic matter with nakdong river with molecular weight of 1,000. What kind of organic matter do you think it is? What kind of organic matter do you think it is? 1,000 dart. Algae. Algae is micro size, right? Algae is, we can see the algae. Okay, but thank you, Hanjuno. Thank you. So algae, so we can see. So Dalton size we cannot see at all. Dalton size we cannot see. So 1,000 Dalton is so small. Protein, 1,000 is very small. The virtually is almost, not almost, it's impossible to see. So protein, absolutely right, the protein. So saccharide as well, right? Saccharide, protein, and some lipid, whatever that is. So from organic matter, organic matter from nature. So who knows what that is? So it is very difficult. So it is not necessary to know exactly what they are. So we measure, okay, we only measure levels of concentration in the unit of TOC, milligram carbon per liter. Okay. Once again, nakdong river, 5 to 7 milligram carbon per liter. How about the Han river? This is nakdong river. Han river. Han river is cleaner than nakdong river, slightly. So about 3, approximately 3 milligram per liter for Han river. And 1.0 and 1.5 milligram carbon per liter for Seomjin river. Okay. So then how you actually remove this one if we want? It's very difficult, I mentioned already. But this organic matter is not toxic. Not toxic at all. Okay, so we will get to that. That's the organic matter a little bit later. And then iron. Okay, iron. So ammonia is very toxic. Right? Ammonia is very toxic. But even with nakdong river, there is no ammonia at all. We don't have ammonia in nakdong river. That's the good news, right? That's very good news. So if we have ammonia, once again, it's very difficult to remove it. It's almost impossible sometimes. So what other ions may we have in our nakdong river? What others? sulfate. So 4. So 4. Sulfate, phosphate, PO4, excuse me, PO4. So sulfate and phosphate is toxic. Sulfate and phosphate is toxic. No. And bicarbonate, HCO3 minus. Bicarbonate is toxic. So the major component of iron in Nakdong River are sulfate, phosphate, and bicarbonate. Sulfate, phosphate, and bicarbonate. Those are not toxic at all. So we don't have to remove this one. So Nakdong River has a high concentration of sulfate, phosphate, and bicarbonate, but you don't have to worry about. We don't have to worry about to remove everything. But iron has some portion of the sodium and chloride. What happened? So Nakdong River, of course, has some levels of calcium and chloride. 10 to the 40 milligram sodium chloride per liter, right? So if you buy the bottled water, 생수, bottled water, please look at how high they have this the sodium and chloride. So 10 and so up to 140, it doesn't matter. It's okay to drink it. How high we have this sodium and chloride for the seawater? For the seawater, how high? Can you guess? So feeling is sometimes very important. Not for the scientists, but we are engineer, right? We are not engineer. We are engineer. So the feeling and sense is very important, I believe. 1,000 level, that's good. That's good. Okay, a little bit high. Okay, a little bit high. A couple of thousand, 3,000 and 5,000. So approximate that. How can you remove sodium and chloride? It is almost impossible. So we have to use a membrane. So 2 weeks from today, we are going to study the membrane process. Not today, but so membrane is nothing but some filtrations with the paper types of filtration. Our mask is our mask for mask against COVID-19. It's also the membrane. Membrane, by definition, can remove a certain size of a contaminant. Okay, certain actually penetrate into pore of the membrane. Membrane has pore. Membrane has pore with a size. So the mask is membrane with the pore size. What? For COVID. Okay, if I ask you, so if you wear the mask, 80% remover. Okay, remover. What is pore size of the mask? If I ask you what is pore size of the mask membrane we are wearing to protect the virus of COVID by 98%. Please use this table. Please use table. So COVID is the virus, right? Okay, virus. So the 차주노 0.05 micron, 이창주 0.01 micron. Okay. Is it true? So I may say that 98%, 98%. So please look at this table. Please look at this table. This virus COVID, to remove 98%, not 100%, 98% is corresponding to 0.02, right? 0.02, yes, 0.02, approximately. So this is a conceptual design, I believe. Okay, please understand the size discrepancy, the size differentiation of the physical process. If you were, so another question, so I would like to give you another question. If we wear a mask with the pore size is 1.1 micron, 0.1 micron, and then the mask can remove COVID. Wait a second. Thank you for your waiting. By 80%. Okay, so please look at this the question. If you wear a mask with the pore size of 0.1 micron, which is this, right? Which is this, and COVID, the virus is smaller than the pore size. Virtually, our mask actually cannot protect any of this COVID virus. But we measure, we can remove 80% of the COVID virus by our mask with a pore size of 0.1, much bigger than the virus size. What happened? Why the fouling? Okay, fouling maybe, but removal mechanism. I'd like to ask you removal mechanism. What happened? Why those masks remove the virus? Even with the larger size of a pore, but come up with a very good job in removing 80% of a virus. So if you wear some handmade mask or handkerchief types of the mask, we can still remove the virus. What kind of mechanisms? Saliva. What is saliva? Okay, I'm sorry not to understand this saliva. What is a saliva? Okay, sorry for my bad English. So I'm always not happy about my English. The friction, okay? Friction. Okay, that's good. The friction is good. A little bit more. Virus hit the surface instead of getting, okay. That's possible. That's very good. Okay. What else? Okay. the electrostatic. What do you mean by the electrostatic? So a more easy terminology can be used. Water block pore. Okay. So maybe, okay, it might be right, but some terminology better than that. Electrostatic. There are a couple of mechanisms to remove a virus. Okay, so first one First one, electrostatic charge repulsion, right? Charge repulsion. So the virus, what charge over the surface of the COVID virus? How about the colloid surface? How about the bacteria surface in terms of charge? Electrostatic the valence negative, right? So that's the natural. The colloid has a negative charge. Generally, at neutral pH, at the neutral pH, all the natural material has a negative charge. Not exception to the COVID virus. The virus has a negative charge. Our mask with the big size of a pore has a negative charge. So a negative charge and negative charge can repel each other, right? So that's the electrostatic interactions. Negative repel each other. Not attract each other. Instead, they reject the virus from the surface of a mask. Exactly same, right? Exactly same to water treatment as well. If our colloid, if our virus, if our dissolved organic matters has a negative charge in water, if we use certain surface having negative charge, we can remove. That's electrostatic interactions through charge repulsion. So if I ask you, so this is very important. So I promise to give you this the problem in your quiz examinations. So this is that much important. Electrostatic, okay? Electrostatic interactions. Okay, negative charge can be used to remove some contamination, including virus, colloid, and dissolved organic matter. Okay. The second, absorption. Right? Absorption. On the surface of a mask, some virus can attach to that. So after using mask, we clean our mask, or we oxidize and disinfect our mask from time to time, or replace newly. So that's why we have observed the virus on the surface of that. Exactly same to our water treatment. If you use some absorbing material to remove colloid, and then surface of that absorbent, absorbent, then we clean those surface after using with colloid. What's the typical absorbent, typical absorbent available to remove colloid and other organic matter, other contaminant? What could be a typical example of this absorbent? Take an example from your purifier, 정수기 purifier. What could be corresponding to this adsorption process as an adsorbent? What could be? Example. right? Soot, activated carbon, soot, has a relatively higher surface area to be used to remove contamination on the surface through mechanisms of adsorption. So there are two different the mechanisms to remove even for a contamination having very small size, but we use electrostatic interactions, charge repulsion, and we can use an absorbent 합착제 such as activated carbon and soot. Okay, so actually we use this activated carbon in the various water treatment plant in Busan, in Daegu. They use this soot, activated carbon, to remove organic matter. But generally, they don't, water treatment plant, they don't have these types of activated carbon because activated carbon is very expensive to be to feed those the treatment process. But Nakdong River, once again, is specifically very has relatively dirty water from industrial sectors, industrial factories. So sometimes they have a very dirty and presumably potential toxic organic matter from industrial factories. That's why they use these activated carbon for their water treatment process. Okay. So that's the major process too. Okay. How about the coagulation? So getting back to coagulation. Colloid are stable. So we define the colloids are stable in that they suspended almost forever. Colloid matter suspended in water. So we don't want to drink a colloid because the turbidity, turbidity is very high. Looks dirty. They actually maybe not, but we don't want to drink that colloid as it is. That looks dirty. So a colloid is suspended, and then we define those conditions as stability. So we would like to de-stable. We would like to destabilize colloid. What do you mean by that? The stable, fluctuations. That's right. The stable colloid stay there forever, but unstable colloid actually gave up their stability to get together to make a big colloid rather than small, and then they finally can be settled down. Okay, the colloid so they suspended forever, but that's the we define stable. But colloid plus colloid plus colloid okay. So 3 and 4 and 100 colloids get together to form the flux. The flux is much bigger than a colloid. The flux formation, we define that as what? Destabilizations. So colloid is a negative charge, right? Colloid is a negative charge. another colloid is a negative charge. They repel each other. That's why they are stable. So if we insert positive charged chemical in it, into the water having the colloid actually bridge to another colloid through these coagulant chemicals to be destabilized to form a flux, and then they can be settled down to be removed out of water. Okay, that's the coagulation process, flocculation and coagulation process. Please understand, you don't have to exactly explain this one. So colloid is stable, looks dirty, with the unit of turbidity, as I mentioned earlier. Why they stable? They are negative charged. Negative charged, the colloid and negative charged colloid, they repart each other to stay water forever, which we define as the stable condition. And then we add the chemical name coagulant, which has positive charge. And these coagulant chemical bridge, connect colloid and another colloid to make a flux, okay? To make a flux, which has a much higher size and finally can be influenced by gravitation higher than buoyancy force, and to be removed through a settlement. And then we can remove this colloid. That's the coagulation process. Okay. Any questions about? Okay. And then salt. Finally, salt. Na. Okay. How we remove this sodium and chloride? How we remove this sodium and chloride? Electricity. Okay. What kind of electricity? So what is the size? Electric charge? Okay, that's fine, but not enough. So if you have a membrane with a very small pore, right? So membrane with a very small pore is not enough to remove sodium and chloride. These types of membrane is enough to organic matter, right? Organic matter is relatively easily removed by membrane process, like in purifier, 정수기 at home. But with the sodium and chloride, with the seawater, not enough. So the Lee Jung-suk mentioned reverse osmosis. This is another membrane. It's one of a membrane without pore. Okay, without pore. Of course, there is a pore, but if you measure size of a pore, there is virtually no pore at all. So a reverse osmosis membrane, generally RO, is non-porous membrane without pore. Of course, there is pore, but very, very, very small pore. Okay, that's the desalination process. RO, with RO. Okay. So Middle East, Saudi Arabia, Arab Emirate. So they've been using this RO process, RO membrane process, to make safe drinking water with seawater. They can remove sodium and chloride in an efficient way, but with high pressure, of course. So reverse osmosis membrane needs super duper high pressure to push the water against osmosis pressure. Osmosis pressure. That's the problem. So we need a lot of high energy demanded to produce enough water against the osmosis forces with the seawater. That's why desalination process is very expensive, the process. Okay, so we've been through this one. So there are only one left before. What is it? Only one left before drinking, only one. So we can remove a particle. We can remove bacteria. We can remove a colloid during the process. We can remove organic matter. We can remove the salt. But we have to make sure our treated water is safe enough to be drunk by the citizen. So what could be? What could be confirmation step? What could be compensation? Killing by disinfection, right? Disinfection. So what kind of chemical can we use for disinfection? To kill bacteria, to kill virus. Green, ozone. What else? Chlorine dioxide, fluorine. Okay, fluorine. Okay, possibly, but generally we don't use this one. This is expensive and has some kind of the byproduct. Okay, that's good. Fluorine. Okay, and hydroxy. Okay, hydroxy radical, chlorine dioxide. Okay, so to make sure. So we've been through what kind of contamination do we have in our source water to make a safe and clean drinking water. And we understand the size of approximate the size of those contaminations, from particle to colloid to dissolved organic matter and salt. And then we would like to understand the mechanisms to remove those things. So then from next class after midterm examination period, we don't have any class next week, and then we would like to step by step. I'd like to give you a little bit more detailed information and detailed knowledge about removal process from coagulations, adsorption, the membrane process, and disinfection. Okay, so this is introduction of this class. This is introduction of a class. So conceptual understanding is more than enough for you to understand, because this is introduction to water treatment process. Water treatment process needs 1 semester, of course, but this is only introduction. So the conceptual understanding is more than enough. Okay. Any questions? Any questions? It's fine from now. So we have 10 minutes left. Any questions? Do we have a midterm quiz? You mean next week? No, we don't have any quiz. So we have a quiz from my parts at the May 4th. May 4th. Thank you for asking. We don't have any quiz next week. Thank you. Let me ask you, so how much 1 ton of drinking water? In Korea, how much 1 ton of drinking water? 1 ton, 1,000 liter. How much in Korea? Okay, 1 million won. 1 million won is 100원? 100만 원, 100원. 삼다수 100, 1,000원. 삼다수, how much? How much 삼다수? It's only, yes, only water. 2만 원. Okay. Please guess. 삼다수 is 100 milliliter, right? 100 milliliter. Okay. 삼다수 is 100 milliliter. Is about 1,000원. Okay. Right? Once again, water 1,000 liter. 1,000 liter. $500. Okay. So do you think it's cheap? Do you think it's cheap? Too cheap or too expensive? So European countries has about 2,000. 2,000. European countries 2,000. One. But we are 100, 500. So I'm not sure. So I'm not arguing or I'm not insisting we are too cheap. So the public sector service types of facilities. So there's no right answer, the robust answer to decide which one is cheap and which one is expensive. But compared to other countries, even in Japan and China, so Korea has the water prices is kind of cheap. That's why we never save our water, right? During shower, so we can enjoy shower as much as possible. Okay. So when you go to Middle East, so they use a desalination process. What could be their prices for their water? Okay, much expensive than us. Much more expensive than us. Okay. That's the other economic consideration should be taken, I believe. So think about our prices, 500 Korean won is appropriate or not. So the US is much higher in price than us and European country. So they suffer, especially in California. So water shortage problem is very severe, especially San Diego. So Los Angeles is kind of the different, but San Diego is been struggling with water shortage problem. So they how much they actually discharge from the wastewater treatment plant, and then the pump into the dam side, and then to be reused for their drinking water sources. So we don't use the wastewater treatment, the discharge after treatment, to be used all over again for our water treatment, right? We never used wastewater for our drinking water source. But the San Diego and many countries as well around the world, which have a problem of water sources enough. So they've been using wastewater, okay, for their drinking water sources. So that's true. That's true. So right now, so we are lucky, I believe. So our process is low. Water quality is relatively good compared to other countries. So, so that's why I would like to discuss with this issue. And sometimes we have a very limited time to discuss, but I'd like to bring those issues into this class as well. Okay, so thank you very much for your attention, being aggressive in responding to my questions. There are limitations to discuss with this one, even through Zoom, but okay, thank you for your attention. Good luck for your other examinations, and see you 2 weeks from last Tuesday. Thank you very much. Okay, good day. Good day. Thank you. Thank you. Thank you.